All I'm saying is and that's what plays and then you have a placeholder for the well, you know, like if you would say, your answer
Yeah, I'm not.
do the same.
I don't think I'm in a
Placeholder.
You're doing this in.
It could be anything. It doesn't necessarily have to be a user input. It could change every iteration. It's just a placeholder.
Yeah, but you want it to change after every
Well, that's just a matter of form.
Yeah.
It's a matter of notation. That's how you can get it to the end.
Good morning, everyone. Once again. Oh, we are live. Okay. So, hi, everybody. Notice the TARDIS has landed downstairs, the ECHQ stand. Interesting stuff there. If you want to go and talk to them. Soon, client. Anyway, more applications of Euler's criterion. So let's just do a quick recap. The Legendre symbol. NP. And then read it as the Legendre symbol of n modulo p. This is a kind of an indicator function. Not really interested in the zero case. This is where p divides n, or i.e. n is congruent to 0 modulo p. We're really interested in it for the other cases where n is a non-zero modulo p. It's plus 1 when n is a quadratic residue mod p. I.e. that means there exists u such that n is congruent to the square of u mod p. And it's minus 1 when n is not a quadratic residue. It means there does not exist a u such that n is congruent to the square of u. Just like a quick reminder of the relevant terminology and the key definition of a quadratic residue. Yeah. Now, last time we proved this nice result, Euler's criterion, which gave us quite an insight into what value this has in terms of n. Or you can kind of view this as a way to calculate the Legendre symbol. And if you're just working with the definition, your way to calculate the Legendre symbol is to go ahead and search amongst the congruence classes mod p, find the ones that are quadratic residues, and inspect to see if n is amongst them. Yeah. And at the moment, finding the quadratic residues, the only kind of technique we have is to take all the congruence classes mod p and square them, and just see what comes up as squares. Have I got a mistake up there? No? Is there a mistake on the? No. All right. Okay. Anyway, so Euler's criterion then is a good step forward from that. Rather than just naively, inspecting everything and squaring everything to see what quadratic residues are, Euler's criterion gives us, in some ways, like a formula to apply to evaluate NP to find out if it's plus or minus 1. Now, but it's more of theoretical interest. It's more that this is going to be useful to us to prove things about quadratic residues, rather than as a way to, in practice, work out whether a given n is a quadratic residue modulo p. And I won't rehash the proof of it, but just to remind you, or try to jog your memory or give you the key message, it was proved by using Fermat's last theorem, Fermat's little theorem. That n to the power of p minus 1 is congruent to 1 modulo. So that means when you do n to the power of p minus 1 over 2, it means you're taking the square root effectively at this side. So that tells you n to the power of p minus 1 over 2 is equal to plus or minus 1 mod p. Investigate that. I'm kind of rehashing the proof now. Investigate that. You find that the quadratic residues must be the solutions to n to the p minus 1 over 2 equal to plus 1, congruent to plus 1. The quadratic non-residues must be the solutions to n minus n to the power of p minus 1 over 2 congruent to minus 1. So proved using Fermat's last theorem and Lagrange's theorem on the number of solutions to polynomial congruences. That one sentence is kind of an encoding of the proof, in terms of revision and getting ready for an exam, just in case you're asking an exam to prove this. This really boils it all down to one sentence. You prove it with reference by making use of Fermat's last theorem, which is this fact, and you should hopefully spot the link to get to n to the power of p minus 1 over 2. You're taking the square root or raised to the power of half both sides, and with reference to Lagrange's theorem on the number of solutions to polynomial congruences. Okay. So this thing congruent to plus or minus 2 would only have p minus 1 over 2 solutions. So we already know this p minus 1 over 2 quadratic residues, p minus 1 over 2 quadratic non-residues. And last time we already saw, this is why I was messing around with the title up here, we already saw the first application of this. Which once and for all settles the case of what the residue status of minus 1 is. Minus 1, or think of that as p minus 1. Is minus 1 a quadratic residue or not? Now we saw when we investigated the initial examples, the initial primes, 3, 5, 7, 11, 17, etc. In a couple of them we noticed that minus 1 was a quadratic residue. P minus 1 was a quadratic residue. In a couple of them it wasn't. So it obviously varies. And this told us exactly when it was a quadratic residue and exactly when it was a quadratic non-residue. Remember, p is an odd prime, so p is bigger than 2 in all of this discussion. So every odd prime number, well, every odd number is congruent to either 1 or 3 mod 4. And so it's quite a direct, simple, explicit characterization. P is congruent to 1 mod 4, and minus 1 is a quadratic residue. If P is congruent to 3 mod 4, then it is not a quadratic residue. Okay, so another application. In a similar vein, is we're going to decide on the classification of 2 mod P. Okay. So this is theorem 8.6. Before we do this, any questions just on that quick review? Anything I could clarify or clear up for you? A quick rundown of the last few lectures. Anybody unclear about anything? Clarify something. So, how do we do this? Well, proof of what I haven't said what the result is. let's just write the result. Again, it's a similar kind of result, except this time it's based on the classification of P modulo 8. Again, modulo 8 isn't that hard to judge. 8 is 2 cubed, so that means 1,000 is congruent to 0 mod 8. So if you look at the prime number modulo 1,000, that means you're just looking at the last 3 digits. So you can judge the congruence class of any number just based on the last 3 digits and the least significant digits, hundreds, tens, and millions. So it's even presented with a gigantic number, it's easy to work out what it is mod 8. You just inspect the last 3 digits. And this classification goes 1 or 7, isn't it? Remind myself. Yeah, 1 or 7, so plus or minus. So it's 1 or 7, or a common way to write that would be plus or minus 1. And this is 3 or 5, or a common way to write that would be plus or minus 3. It's kind of a tidier way to write it. Okay. Okay, so it's based on the classification of P modulo 8. So how do we prove this? Okay. Well, so straight away we bring down Euler's criterion. Okay. Euler's criterion says, in this case, that the Legendre symbol 2 mod P, whatever it is congruent to 2 to the power of P minus 1 over 2 modulo. And the idea to the proof is to investigate this in a couple of different ways. So look at 2 to the power of P minus 1 over 2 in 2 slightly different ways. And in so doing, we'll connect 2 things that will give us the result. Sure. The first way to do it, and the way we do it in both cases, is to multiply together all the evens from 2 to P minus 1. Remember, P is an odd prime number, so P minus 1 is even. So we're going to take all the even numbers, 2, 4, 6, 8, yada, 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 and P minus 3, P minus 2. Okay, so that's them all multiplied together. And they're all even. So a very straightforward move we can do on this is to take the factor 2 out of all of them. Yeah. Each one is even, so you can suck a 2 out of each of them, and actually that will give you 2 to the power of P minus 1 over 2. So out of each of them you take a load of, you take 1, 2 out of each of them, and of course what you're left behind is 1 by 2 by 3 by 4 by P minus 3 over 2 by P minus 1 over 2. How many 2's have you taken out? Well, it comes down to how many numbers are here in the product. Well, you can just see it here, so count it. 1, 2, 3, 4, P minus 1 over 2. So there's P minus 1 over 2 factors. Because it's all the evens from 1 to P minus 1, and half of them are even. So there's P minus 1 over 2. Okay, so that's just like primary school arithmetic, isn't it? But it's bringing out the term from Euler's criterion. So what you've got here is 2 to the P minus 1 over 2, and we know this thing here in the bracket by a slightly more sophisticated name. This is the product of all of the integers. Remember, these things look like fractions, but they're not, they're integers, because they're even numbers in the numerators, so we divided by 2. So here you've got a factorial. Okay, so you've got all the numbers, but all the numbers, the odds and the evens, from 1 to p minus 1 over 2, multiplied together. So this is p minus 1 over 2 factorial. My brackets go there, yeah, so I mean the factorial is only on this. Just for the sake of no ambiguity. Okay. Okay, so that's one way of looking at the product of all the even numbers. Inside it, we discover the power of 2 that appears in Euler's criterion, and we see this interesting factorial. So now we're going to look at the product of all the evens in a slightly different way. Does anybody need clarification on any of that?
Where's p minus 2?
Where's p minus 2?
Yeah, we can see.
Where is it? Why haven't I written it down? So what am I doing here? Remember, what is p?
It's odd.
P is an odd prime number.
Yeah.
So here I said I multiplied together all the evens. So the first even is 2, second even is 4. The last even is p minus 1. What's the second last even? It's p minus 3.
Right, yeah.
P minus 2 is an odd, so p could be 11.
Yeah.
So the p minus 1 is 10, but the next previous odd number is 8, so it's p minus 3, isn't it? Yeah.
Just odd minus evens, odd time minus odd.
Yeah.
Just, yeah.
Yeah, so you're just stepping back from the last even number, but you have to step back 2 each time, so you just want to land on the evens. Yeah. And then here I'm taking out all the factors of 2, so take out 2, 2, 2, and well, this is just how I represent it. It's p minus 2 over 2 that's left behind, and you take out a factor 2, and p minus 1 over 2 that's left behind. So you get a factor 2. Okay? Yeah. Yeah.
Wouldn't the factorial then still account for the p minus 2 over 2? How can you say that the factorial of p minus 1 over 2 excludes p minus 2 over 2?
Yeah, well, I think you're kind of thinking of it as the factorial of p minus 1.
Right.
It's not. It's the factorial of p minus 1 over 2.
Yeah.
So when you do a factorial of n is n times, what's the next number? N minus 1.
Yeah.
Okay. So this is the n. And what you get when you subtract 1 from this?
Yeah.
You subtract 2 over 2.
Yeah.
So you got a p minus 3. Yeah. And it's just you're not used to counting backwards in halves. You should do that a bit more.
Also, p minus 2 over 2 is not an integer.
Yeah, indeed.
So it can't be a factor.
Yeah, we'd be worried that p minus 2 over 2 was appearing here in our integer expression because it's not an integer, is it? Yeah. So I think when you straighten that out in your mind, you'll see it's quite, it's elementary. Okay, so now we want to look. So now this is the kind of imaginative, creative bit that they did to put this proof together. You look at this product of all the evens, but in a slightly different way. So all these evens here, I'm just going to rearrange them like this. So I'm going to take one from the end and one from the beginning. Then the next one from the end and the next one from the beginning. And the next one from the end, the next one from the beginning, and so on. Now I'm going to look at them in a modular way. On the p minus 1, this is all these congruences are going to be mod p, of course. P minus 1 is simply, that's congruent to minus 1. Two is still 2. 2 is 2, of course, but I'm going to think of that as having a minus 1 squared. So this, for reasons that will become clear, I'm going to write this as 1 multiplied by minus 1. P minus 3 is minus 3. I'm going to represent that as minus 1 cubed. 4 is plus 4. I'm going to represent that as minus 1 to the power of 4. 5 is minus, p minus 5 is congruent to minus 5. The minus sign I'm going to create from minus 1 to the power of 5. So I'm choosing a modular representation of all the even numbers, but they're alternating in sign. Okay? They're alternating in sign. So the ones from the end of the list get counted with a negative sign. The ones from the beginning of the list get counted with a positive sign. And somewhere we meet in the middle, but we don't know, we can't say for definite whether the middle one, or we don't even know if there is a middle one. There's either p minus 1 over 2 is even, in which case there is no middle one, they split into 2 halves. Or p minus 1 over 2 is odd, and there is a middle one. If you start from the last, in which case it's going to be a negative. So the last thing we consider here is S. Well, it's p minus 1 over 2, it's the one in the middle. And it's congruent to, well, I'm going to say it's congruent to, it's either going to be plus or minus of itself. And it's p minus 1 over 2. The S is a bit superfluous there. Yeah, let's see. I've written an S in the notes, but it's a bit. Well, yeah. No, the S stays. So where S is either p minus 1 over 2 or p minus 1 over 2, depending on whether p minus 1 over 2 is odd or even. So let's just write out a couple of examples. So p equals 7. You look at all the even numbers. You got 2, 4, 6. So here I'm going to take 6 as being congruent to minus 1, 2 as being congruent to plus 2, and then the 4 gets picked up as being congruent to minus 3. Okay, so the last one appears with a minus sign. Whereas if I took another prime example, I'd have to go to 13. If p equals 13, and you take all the even numbers, then the 12 I'm considering as minus 1 mod 13. 2 I'm considering as plus 2. 10 I'm considering as minus 3. 4 I'm considering as plus 4. 8 I'm considering as minus 5. But the last one in this alternating stepping through them all appears as plus itself, p minus 1 over 2. Because in this case, the p minus 1 over 2 is even. The 12 over 2, 6 is still an even number. So it's to do with whether you've got an odd number of evens or an even number of evens. And you start calling them positive from the beginning of the list, you call them negative from the end of the list, and it's whether there's a 1 waiting in the middle and it gets called a negative, or they split into 2 equal halves in which the first half are all positive and the second half are all negative. Okay. So it's nothing that complicated as such, but writing it down completely generically so that everything is just indexed by p, that's maybe just a little bit, it's helpful to look at a few examples and just think about it a bit to understand what's happening. But now what isn't really apparent yet is why I've Why have I represented these plus and minus signs? See, here I've just written a plus or minus sign plus against the early ones, minus sign against the later ones. Why here have I chosen this curious representation of a plus and minus sign? Well, we can do it. You can see why it's true. Minus 1 to the 1 is minus 1, minus 1 squared is plus 1, minus 1 cubed is minus 1. You understand how it's working, but why? Why did we choose that? Well, we chose that because what are we going to do with all these things? Well, remember what we did with the even numbers before? We multiplied them all together. Well, we're going to do that again. Except now we're not going to multiply the original numbers together, we're going to multiply their modular representatives together. Now we multiply. We got 2 by 4 by 6. So all the evens, all the way to p minus 1 over 2, except now I'm taking them in a modular, a congruence. And what I'm going to do is multiply together all these right-hand sides. Yeah. And that's going to come down in a very interesting way. First of all, you can see I'm going to get p minus 1 over 2 factorial. Because I'm taking 1 times 2 times 3 times 4 times 5. I'm multiplying all these together. So let's forget about the positive and negative signs for the moment and just multiply the integer part, the positive integer part. So you get p minus 1 over 2 factorial, which is nice because we got that before. Remember that came up before, so it's come up again, which is good. But now I've got all these alternating positive and negative signs. Now, what I'm doing there is I'm multiplying together all these powers of minus 1. Yeah? Now, how do powers behave when you multiply a lot of them together? When it's the same base. Yeah, it's just you just add up all the exponents, and that's the new power. So the exponents are, there's an exponent 1 there, 1, 2, 3, 4, all the way up as far as p minus 2. P minus 1 over 2. Now, we know a trick or a method for adding up, well, adding up lots of different, arithmetic series and geometric series we can add up and get easy summation formulas for. So in particular, this is an arithmetic series, particular simple one. You're just adding up all the integers from 1 to some endpoint. So just to remind you, if you add up 1 plus 2 plus all the way to, say, n, hopefully everybody just reels that off. What's the sum of all the first m integers? M times m plus 1 all over 2. Yeah. So this story from Gauss. When Gauss was a school child and the teacher gave them this sum to do, expecting them to sit down patiently and add them all up, counting on their fingers or something. So the simple explanation is you notice that when you add 1 from the end and 1 from the beginning, you get m plus 1. And you get that all the time, because then the next pair is 2 plus m minus 1. You still get m plus 1. 3 plus m minus 2, you still get m plus 1. How many m plus 1s do you have? Well, you're pairing them off, so you got m over 2. Straightforward. But it's an instance of the arithmetic sum formula. Any series which increases by a fixed set amount each time, here 1, but any fixed step size, you can always write down a nice summation. So that's what we got here. So we can write this down. This is going to be, now what's our final number? Our final number is p minus 1 over 2. So p minus 1 over, let me put these in a cloud and say that this cloud is equal to, so what? It's n plus 1. So that's going to be p minus 1 over 2 plus 1. Well, plus 1 is plus 2 halves, so it's going to be p plus 1 over 2. And then you've got a m over 2, which is p minus 1 over 4. Isn't that right? So the n here is p minus 1 over 2. So the m plus 1 is p plus 1 over 2. The m over 2 is p minus 1 over 2 divided by 2 again. So p minus 1 over 4. And we can tidy that up a little bit. You've got over 8, and it's p minus 1 by p plus 1. Well, that tidies up to p squared minus 1 over 8. Okay. All of these congruences, of course, are modulo p.
Because I take it modulo 4 as well.
Take the exponent modulo 4.
No, as in over 4. You know, it's like in our end result, we've got modulo 8. Because we've got that.
No, so this is divided by 8, so that's just a 4 by 2.
Yeah, I know, but I mean, if you times the right by 2 instead.
Well, this is, no, so I have to stick with modulo p because...
No, I don't mean modulo p, I mean the 8. You know,
This 8.
yeah, you've done it by times and 4 and 2 together.
Yeah.
And you could have just times the right side by 2, get 4 over 4. Oh wait, sorry, is that minus sign 2?
Here.
Yeah, no.
These are these two fractions
Then
multiplied
times
together.
sorry,
Multiplied
that's
together.
Yeah.
Yeah, because it's like up here. I got m plus 1 multiplied by m over 2. Sorry. Yeah. Sorry, yeah, it's a bit small then. Is there anything else? Now, we've become a bit immersed in it. We need to stand back now and see what we've done. We've got this result here, which is all the evens multiplied together. And it's congruent to this here. But before we had all the evens multiplied together, which was just the right-hand side is at the top of the page here. We had all the evens multiplied together. Well, this wasn't a congruence. This was just a straight equation, and this was equal to this. So I'm going to call this equation star, and this equation star star. And I'm just going to put them together, okay? Because they're both representations of the product of all the evens. This one is an exact equation. This one here is a congruence mod p. So we can say now joining star and star star. So we got the product of all the evens, which we're not so much interested in now. What we're really interested in is that this is equal to 2 to the power of p minus 1 over 2 by p minus 1 over 2 factorial. Okay, that's star. And the star star expression is the same factorial by minus 1 to the power of p squared minus 1 over 8. And this congruence here is modulo p. So now we kind of forget, or we don't really care that this is where it came from. What's important now is this congruence between these two, okay? Because remember, this is the thing that appears in Euler's criterion. 2 to the power of p minus 1 over 2. And the residue status of 2 modulo p, the Legendre symbol of 2 mod p, is congruent to this, 2 to the power of p minus 1 over 2. And here we have it involved in a nice congruence with something over here which we hope to be able to evaluate. Now, what's our temptation here?
To divide what we can't necessarily.
Yeah. To divide what? To divide.
Factorial.
Yeah. So our temptation is to cancel the factorial. Okay. Good. So why is it? Yeah. Why do you have to be careful about that?
We don't know if it's got an inverse.
Yeah. So we need to know that it has an inverse. So remember, if you've got two things congruent and you spot a common factor, you can cancel them provided the thing has a multiplicative inverse, because that's how the cancellation is effected, is carried out. You multiply both sides by the multiplicative inverse, and that cancels it away. Does this have a multiplicative inverse modulo p? What's the criteria for when something has a multiplicative inverse modulo something else? What equals that?
So you have some element time, well. some-
Yeah, no, that's the definition of a multiplicative inverse.
Sorry, what you're asking.
What's the criterion that allows you to decide whether such an inverse exists for something modulo something else?
The GCD, the 2 is 1.
So the number you're investigating has to be co-prime to the modulus. If it's co-prime, there is an inverse for it, which you can draw down. If there isn't, then it doesn't exist. So is this number co-prime to the modulus p?
Yes,
Why?
because P is prime, that number's smaller than it, so it can't divide it.
Well, no, this number is probably bigger than p.
After.
It's the product of all. This number is big. Okay, so it's very much depends on the fact that p is prime. It's good for start. That limits the number of the common divisors, because it can only be 1 or p that you could have with p.
So none of the factors will have to give it.
So this number, although it's probably pretty big because it's a factorial, it's a big product, it'd be well bigger than p. But you're right. This is made up of factors which are all less than p. Yeah, p is a prime number. You can't magic up or generate p by multiplying together smaller things. It's a prime number. It's very much not that kind of thing. So no matter which number is smaller than p you're multiplying together, you never generate a factor of p. So there can never be a common divisor between this factorial and p. Okay. So boom, we can cancel it. So remember, this is the Legendre symbol. So we better justify that. Since p minus 1 over 2 factorial has a multiplicative inverse, modulo p, as it is co-prime to p, as p is a prime. The factorial is just a product of numbers less than p. So whatever product you get out of multiplying together numbers less than p has to be co-prime to p. Because you can never manufacture p by multiplying together smaller things, because it's a prime number. Okay. And I've just reintroduced our Legendre symbol again, because remember, this is Euler's criterion. It says this is congruent to this, mod p. So then this is congruent to this. So just cutting out the middleman now, this is congruent to this power of minus 1. In fact, slightly better than saying they're congruent, because they're both by definition things that are plus or minus 1. Legendre symbol, when we defined it at the very beginning, it's either plus 1 or minus 1. This is a power of minus 1. It is either plus 1 or minus 1. So the two things, not only are they congruent, they're actually equal. Yeah? Equal to minus 1. P squared minus 1 over there. As both are plus or minus 1. So there's no ambiguity of being congruent to, differing by a multiple of p. They're exactly equal to. So we're almost there. This is, surely we can get a handle on the value of this. And yeah, so now examine closely this right-hand side. I think in the proof in the notes, I've laid out a quick table. What are the options for p modulo 8? Well, to begin with, you think you've got options 0 to 7 mod 8, but some of them can't appear for being an odd prime. So you can't be 0 mod 8 if you're a prime. You can't be 2 mod 8 if you're an odd prime. Yeah, because you're divisible by 2. You might be 3, but you can't be 4. If you're 4 mod 8, you're divisible by 4. You might be 5, but you can't be 6, because if you're 6 mod 8, you're divisible by 2. But you might be 7. So the only options are 1, 3, 5, and 7. Because P is an odd prime number. So then you just look in each case what P squared minus 1 divided by 8 is. So P is 8Q plus R, and R is equal to 1, 3, 5, or 7. Some Q. So P squared minus 1 is going to be this squared, which is 64 Q squared plus 16 QR plus R squared minus 1. And you can divide this by 8. You can divide a fair bit of it by 8. And then you've got remainder R squared minus 1. And so now you just look at what you've got in the different options. So P, R is 1, 3, 5, 7. If R is 1, this is 0. So the whole thing is just 8 times this bracket. Fair enough. If R is 3, then this is 9 minus 1 is 8. So this P squared minus 1, it's going to be 8 times the bracket. Plus we add an extra 1 into the bracket because we got 8 here. No, add the 1 to the 8 times the bracket. So it's still 8 times the bracket, then it's just plus 1 after I divide it by 8. Oh, sorry, that's not a good way to lay it out. So P squared minus 1 over 8 equals, let's lay it out this way. So this is R equals 1, R equals 2, R equals 3, R equals 2, 3, 5, and 7. When R is 1, we get 8 times this bracket plus 1. When R is 3, when R is 1, we get 8 times the bracket. When R is 3, we get 8 times the bracket plus 1. Fair enough. When R is 5, what you get here? You get 25 minus 1. Or divide 24 by 8, you get 3. So it's 8 times the bracket plus 3. When R is 7, you get 49 minus 1, which is 48. Divide 48 by 8, it's 6. So it's 8 times the bracket plus 6. This number I can say is even. This number I can say is odd, because it's 8 times something plus 1. This number is definitely odd again, and this number is definitely even. And remember, I'm only interested in P squared minus 1 over 8 because it appears as an exponent on minus 1. So I only need to know whether it's odd or even. Yeah. So this gives us our final result. Remember, these are R equals 1, 3, 5. These were the thing of R being plus or 1 or 7 mod 8. And 3 or 5 mod 8. So we got plus 1 here and minus 1 here. Because you've got your minus 1 to an even power in these two cases, plus or minus 1, 1 or 7. So it's plus 1. And you got minus 1 to an odd power. So 3 or 5. So when P is 3 or 5, modulo 8, you got minus 1 to an odd power, so you got minus 2. So it's just 2. I wrote n back here a few times. Of course, it's always 2. N is 2. So this establishes it's another application of Euler's criterion, and with some clever manipulation of the even congruence classes, we were able to hammer this out. Okay. So the residue status of 2, remember from our initial example, sometimes 2 is a quadratic residue, sometimes it wasn't. So there's obviously some classification to do. It turns out to turn on whether what P is modulo 8. That's easy to evaluate if you're given a prime number because it only depends on the last 3 digits. Thousands and higher powers of 10 are divisible by 8. So we've got a straightforward way now to decide whether 2 is a quadratic residue modulo P. Remember, our long-term aim that we want to get to, we'll get to it in a few lectures, is to have a general method that can tell us what any n modulo P is. And tell us the residue status of any n modulo P. At least now we've ticked off -1 and 2. And we're starting to see that there might be some systematic behavior going on which we can hopefully exploit and capture. Okay, so I'll be seeing you again tomorrow. Quickly review this tomorrow, see if there's any questions about it, and I might say a little bit about the quadratic reciprocity principle tomorrow. I'll say a bit more about it. Okay, thanks for your attention.